All right. All right. I will begin. That was not my plan, but it worked. So there we go. I'll begin with a word of prayer. Dear Father, we thank you for this day. Again, I thank you for these students, this class. Just ask you to be glorified in what we do, and that we understand a little bit more about your creation today together, Lord. In your name I pray, Lord Jesus. Amen. Yeah, if any of you misbehave, that's fair. Pretty well, so imagine if you that. Oh, excuse me. Oh. All right. So, let me talk a little bit, just in the abstract, about conservation laws. So at this point, we've proved, that we want to conserve net mechanical energy, right? So we've looked at some at that, like we have the rotational plus the kinetic for some systems that we want to conserve. We'll look at some examples of that today. That's the one thing. Conserve net mechanical energy, like, so here you have energy is kinetic energy, translational, right? Plus kinetic energy, rotational, and then plus any potential energy, right? And for us, typically potential energy is just gravity, but the concept of potential energy, of course, is more general than just gravity. So that's one. Now, is energy always conserved? No, right? But oftentimes we have problems where we can use conservation of energy and perhaps also, energy loss due to friction in a meaningful way to tell a story about solving some problem. The other thing we've talked about, of course, is conservation of linear momentum. And so there we have, basically the big story is that big dp dt is equal to the net external force on some system, right? So basically dp is equal to the external force times dt. And so if either the external force is 0 or if dt is, dt small, right? Then you get that the change in momentum is essentially 0. So this gave us the initial momentum was equal to the final momentum. So this is like before collision, after collision, right? We've done these. When is momentum conserved in a collision? The answer is yes, all right? So a collision by definition is something that happens so quickly that there's no time for forces to change momentum in the process, right? Now, if you ask me, is momentum conserved for some system over some finite amount of time, the answer is, well, it depends, right? If there's a net force on the system that can impart a change in momentum, that's what we call an impulse, then sure, like the momentum can change for a system. Like, for example, the system might be a tennis ball, right? If the tennis ball is thrown against a wall and then it ricochets off, then the momentum of the tennis ball is certainly not conserved, right? It's changed from its gravity in its flight and also the force of the wall giving an impulse to the ball as well. So is momentum always conserved? The answer is it depends, right? But for an isolated system where the net force is 0, then yeah, momentum would be conserved. And then we also have conservation of angular momentum. So angular momentum, and basically the big result there that we worked out last time is that the time rate of change of the total angular momentum is equal to the net external torque on the system, right? So again, if the external torque is 0, angular momentum is going to be constant. On the other hand, You might consider situations which are collisions, right? In the collision, the angular momentum has to be conserved as well. So, so example 1, here's a silly example. Suppose you have like a disk, a turntable, if you will, all right? And its radius is r, and it's spinning at initial angular velocity omega naught, all right? So it's sitting there, it's spinning like that, right? And then you take a big, you have a cat, you know, here. And the cat has mass m, right? And let's suppose that the turntable is a uniform disk, and let's let its mass be big M. Right? And then you do what you would do to a cat, right? Which is what?
Pet it.
Pet it. It's not going to work for us today.
Scare it with a cucumber so it jumps on it.
Sir, it really depends on the cat. Like, I once had a cat that only likes me and hated everybody else. So I would pet that cat. So whatever.
These, a guillotine. I like that. That'll work. Or, I mean, I don't want to really give it any kind of motion, so I want like that thing you slaughter animals with that it's just like quick and, I don't know if it's painless or not, I'm not the animal, but yeah, a gun.
Let's go.
So, no. Yeah, the guillotine idea was a good idea. So there's like some kind of platform here, right? And then, and then the platform drops out, right? And the cat falls to its death, of course. And then at the end, the cat's down here. I didn't make it big enough to put the, like, I mean, if we could blow up its face, it would be like this.
We're gonna blow up the cat's face.
So the cat, so at the end,
Do you know what PETA is? Do you know just, do they like try to find you once in a while?
is that people eating tasty animals?
I wish.
So, so the cat drops and it sticks, right? It's a Velcro cat. It's a Velcro covered disc. I mean, choose your story, all right? If this cat bothers you, you could make this a jar of peanut butter, and the peanut butter drops onto here and sticks on the record. I mean, whatever. The point is that there's a mass, it drops onto the disc, which is originally rotating with angular velocity omega naught. The question then is, what's the final angular velocity for this disc after the thing drops onto it, right? That's the question. So how do you solve this? Well, conservation of angular momentum is the way. See, because we're assuming that it's spinning around and that it's spinning in such a way that there's no external torque on the system, all right? There's no frictional force slowing the disk down. It's just sitting there, and it would just spin forever in this hypothetical, all right? So what happens then is we conserve angular momentum. So like angular momentum initial is equal to angular momentum final. In this situation, the initial angular momentum would be I omega naught, and that's I for the disk. The final angular momentum would be I for the disk plus I for cat, omega f. We don't know what omega f is. And how would you calculate the moment of inertia for the cat? Now, it matters where the cat drops. Do you guys want to make the cat drop? Let's make the cat drop. Let's say that the cat dropped. Let me append my picture a bit. Suppose the cat drops like right here. All right, so let's suppose that the cat drops distance 0.8 times the radius from the center point. That's where the cat drops to, okay? And we're going to idealize the cat as a point particle because I didn't give you any dimensions. If you'd like, we can make the cat a cylinder, but let's just leave it as a point.
Falls on his face.
Falls in space. Okay, very good. Very good. That's the spirit of the problem. So the moment of inertia for a disk is what? 1/2 mr squared, right? And the moment of inertia for the cat disk system is the moment of inertia for the disk, 1/2 mr squared, plus mass of the cat, little m. And the radius, all of the mass of the cat is that same distance, 0.8 r from the center, right? So I do 0.8 r squared. And that gives me the moment of inertia for the final system. So in short, solve for omega f. There it is. Omega f is equal to, 1/2 mr squared plus 0.64 little m r squared divided by, oh, I can't do math. Yeah, I know, exactly. Yeah, that's the denominator. Poor choices on my part. But I'm going to reclaim the calculation and divide by r squared since it's everywhere. And so what I really have is 1/2 m, good grief, 1/2 big M divided by 1/2 big M plus 0.68 times little m, all times omega naught. 8 times 8 is 64, divided by 100 is 0.64. The r's cancel, yeah. So there you go. A problem like this has appeared on many of test 3 of my course. Sorry, I'm writing too low. I forgot to bring my glasses. I can't see. There may be CFARs here. If so, I'm sorry. Oh, you. Yeah, you don't belong here. See here. Anybody else? Oh, he? Are you sure? Is this a trap? Example. All right, so. Let us work further examples. I will put numbers in many of the future examples. Let's get going here. So suppose we have a compact disk rotating at 3,000 RPM. What is the angular speed? What's the angular speed in radians per second? Question number 1. And then question number 2 is how fast is a point 4 centimeters from the center moving? So this isn't really an angular momentum question, right? This is just a back to the basics. And we need to do more of these, so the examples today will kind of be eclectic, all right? There's going to be a lot of things here today. Okay, so what's the omega? The omega then is what? We've got 3,000 revolutions per minute. How do we convert that to radians per second? Multiply by pi over 3. Dudes. So 2 pi radians per revolution. Is that right? And then was that what you guys told me? You guys said pi over 3? Is that right? 30. You guys are too smart for me. Let's see here. 60 seconds. Pi over 30. Cool. Yeah, you guys got it.
That's
That's harsh. Man, don't know how to dot product. That's like, man, take it to the hall. I don't know. 314. 314.16.
Yeah, I like to report a murder.
You woke up this morning and you chose war. Let's see here.
There was no peace. Peace was never an option.
So to find the speed, we do radius times omega, right? So the radius in question here is 4 centimeters. So we do 0.04 meters times 314.16 radians per second, and that should give us the angular speed, the speed actually. That works out to 12.16 meters per second. Fun fact, 1 meter per second. 1 meter per second is equal to 2.237 miles per hour, if you work it out. So
That's a very, wow.
So this
That is,
is about 28 miles per hour.
what?
So I was looking back. This is from lecture. Yeah,
12.56, or technically 12.57.
12.57.
The 314.16 times 0.04.
I don't know about that. We're doing live fact check.
All right.
Does Matt check it out?
I was trying to use my notes, but I'll doubt myself. Let's see here. Yeah, he's.
I was at 12.5.
Yeah, you got it. You got it. 12.57. Fair enough. And that times 2.237 is 28.11. There you go. Now, and I looked at this example. This is from my lecture 28, by the way, guys. So I'm going to try to explain the examples. The examples in lecture 28 are great. These are like a really good collection of examples. So we're going to work through these today. But so I looked at this example and I went, 28 miles an hour? Is that right? Is that what a CD really, does a CD really spin? It's like, and the thing is, this isn't even the edge. Like actual physical CDs are 6 centimeters. 6 centimeters, so actually 30% more than this. Like that would mean, so like 40-ish miles per hour on the edge of the CD. Is that, and I thought that's really? So I looked it up, and this is nonsense. Like the actual typical physical speeds are between 200 and 500 RPM. So they don't actually quite spin that fast. But if you'd like to see videos of CDs breaking apart when you spin them that fast, of course such videos exist on YouTube if you want to look them up. I'm sure that's something those slow-mo guys have done, right? But all right, anyway. So yeah, this is like an unphysical, for CD players, that's not how fast they go. So they're more like a sixth of that. So something like maybe 6 to 7 miles per hour, which is, I guess fast, but not as fast. I don't know, whatever that means. Example 3. Suppose you've got a rod that's like this. So you have a rod of mass m, and a quarter of the rod is like that. All right, and it's rotating around a point 25% from one end at angular velocity omega. The question is, what's the kinetic energy of such a rod in terms of L and omega? So mass of the rod is m. So find kinetic energy as function of the length of the rod as well as its angular velocity omega. So can we do this? This is a pretty good problem. No numbers for a change. So I can't be wrong, right? All right. Is it really? That's depressing. It took me a half hour for these two? Good grief. Oh, sad. All right, so the kinetic energy is 1/2 I from the left half omega squared plus 1/2 I from the right half. Well, I say half, but it's really a quarter omega squared, right? Kinetic energy rotational 1/2 I omega squared. So you can divide and conquer, right? You can talk about the kinetic energy of the right half, kinetic energy of the left part. I shouldn't say half. It's not a half, is it? What is it? So on the left, we have 1/2 And what was, if it's rotating around the end of the rod, what was the formula? It was 1/3, right? 1/3 the mass times the length of the rod, which in this case is what? For the left half, it's actually, I keep saying half, but it's bothering me, 3/4, the left 3/4. So 3L over 4 squared. I'm going to factor the omega, I put the omega squared way out here, okay? Goodness gracious, what's the mass of the left part of the ruler? It's not all of m, right? How much m is there? 3m over 4, right? Assuming it's, exactly, assuming it's uniform. Good point. So we'll treat the non-uniform case on the test. So, mostly joking. Let's see here. So 1/2. Why is it 1/3 is a great question. Anybody answer that? Because it's wrong.
There's 3 letters in wrong. No.
There's 3 letters in wrong. I'm not sure what to do with that, but I like it. Oh no. All right, so I'm missing something here. There's a third there because we're talking about a rod rotating around its end, and we worked out that 1/3 ml squared is the moment of inertia for a rod rotating around its end. Around the center, it was 1/12 ml squared, right? But if you're rotating it around the end like this, then it's 1/3. Whee! All right. So I'm missing a third here as well, okay? There's supposed to be a third on both of them. I just forgot to write it in the start. So, work it out. And what do you get? After some arithmetic, you get 7 over 96 m L squared omega squared. There you go. Oh man. All right, next example here. Oh, goodness gracious. Have you guys ever heard of a mechanical battery? How would you store energy mechanically? A spring? Oh, that's a good answer. Duh, I should have thought of that. Another popular way is like with gravity, right? You just, pump a bunch of water up to a water tower. It has potential energy due to gravity, which you can use later, right? All kinds of, a lot of technology, say 300 years ago, is based on this more or less, right? You put up a water wheel on a river, take advantage of the kinetic and potential energy of the water passing through, and you can turn that into a, sawmill or a thing to grind grain or whatever. But there's an idea that's been around for a while, which is a flywheel. So the idea of a flywheel is you've got some kind of mass, right? And you set it up so it can rotate, and it has rotational kinetic energy. And if you can, get it rotating really fast, it's got lots and lots of energy, and it's pretty hard to stop, right? So that's what this example is about. And let me just kind of draw a picture like this here. So it's rotating, let's say that way, all right? And it's got inner radius R1, it's got outer radius R2. I'm giving the mass to be 100 kilograms. and it's spread uniformly over, I say, a hollow cylinder of inner radius. The R1 is 25 centimeters. The R2 is 40 centimeters. All right. And I say, suppose furthermore that the flywheel is revved up to 30,000 RPM. That's pretty generous, don't you think? I mean, I don't want to be anywhere near 100 kilograms of metal spinning at 30,000 RPM. You understand, this would be an incredibly dangerous object to be anywhere near, right? What happens if it fails?
Someone is dying, someone is suing, and we're all concerned.
Someone's dying, someone's suing. It's headed for the hills. Yeah, it's a lot of destruction. Yeah. So here's the question: how far can you drive a car using this energy if it takes 10 kilowatt hours?
Is that real? I think you're good.
How far can you drive a car if it takes, on average, 10 kilowatt hours, which is 10 kilowatts, to maintain 40 mile per hour travel? We'll assume constant speed. All right. So let's work it out. Yeah.
For this, did you say we're assuming we start already in motion?
Yeah, we're assuming constant speed. Yeah. Is 10 kilowatt hours, 10 kilowatts a reasonable power for a car? What do you guys think?
Why not?
Why not?
Is that a Google thing?
Why don't you guys Google average power output of Tesla? Find out for me. I don't know. When I wrote these notes, Teslas hadn't been invented. So, what's the average output of a Tesla? 360 kilowatts.
And,
So this is paltry.
yeah,
360. Dang. So this is a 36th of a Tesla's power usage. All right. So in context, if you get an electric scooter, with a 10 kilowatt motor on it, you can go very fast. Look it up. You can find them. They'll go 70 miles an hour.
What? I need one.
People have taken point of view videos on like scooters going down city streets at like 50 miles per hour. It's.
So who needs a car when you have a...
I mean, that's not transportation. That's a death wish, right? But
Yes, but
anyway.
if my home is in heaven, I'm just taking the expressway.
All right, so let's work it out. The total energy of the flywheel, given these parameters, which I think are very generous, quite generous actually. 1/2 the mass, and this one we haven't worked out, but it's worked out in the notes that I have typed up for you guys. But this is the formula. It's not at all obvious why this is the formula, but 1/2 m. Oh man, oh, there's a quarter here. So half a half is a quarter. This is the formula for I. It's 1/2 the mass times the sum of the squares of the radii. If you've got a thick cylindrical shell, times omega squared. And I won't bore you with the numbers, but when you plug all the numbers in, this works out to 5.48 times 10 to the 7th joules. Or if you like, 54.8 megajoules. And if you calculate how much time you get, so the time that you get, so power is equal to energy per time, right? If it's average, that tells us that the time is equal to the energy divided by the power, which in this case, 54.8 megajoules divided by 10 kilowatts. That gives me, 500 and Oh, my bad. 50 points. Yeah, I'll get it eventually. 5,480 seconds. And so, or AKA about 1.52 hours. So when you find the distance, x times, change in x is v delta t. Everything's constant here, so we just multiply things. We've got 40 miles per hour times 1.52 hours. And that gives us 60.9 miles. Well, I guess my question to you would be, where are you going to mount this flywheel on your scooter?
It's a unicycle.
It's a unicycle scooter. I guess that's not too big. I mean, 25 centimeters by 40 centimeters is relatively small, isn't it? Yeah.
Yeah, and then there's 30,000 rotations per minute.
It's just incredibly dangerous.
All I care about is getting to my job.
The other thing you have to understand is, like, when you try to, like, move this, have you ever tried to move a disc that's spinning very fast, like around its axis? It doesn't. It has a, it don't exactly.
You wish it could, but it won't.
So, but to bring further context to this, and for why anybody who ever tries to sell you on a flywheel battery is just insane. So energy in gallon of gas. Anybody know how much energy there is in one single gallon of gas?
Doesn't it depend on the type?
Probably, but roughly speaking here, let's assume the best.
What's regular? Guys, why not regular?
Let's regular. Something like 130 megajoules. So this crazy flywheel doesn't have as much energy as about a half a gallon of gas. Gas has incredible energy content, which is why it's pretty hard to beat. Yep. Hydrogen? I don't know.
That's what was being crazy.
I mean, the thing about hydrogen is, well, the funny thing about hydrogen is all the all the ways of extracting hydrogen from the to make it usable for like hydrogen vehicles, as I understand, are all very, very carbon intensive, which makes it funny for the people who care about that kind of thing. Which is why we need nuclear energy, sure.
I will die on that hill.
Well, I don't know. See, so joking aside, of course, the advent of lithium-ion batteries has turned, has made electric cars, like, you know, plausible. Obviously, they're all around, right? But there are bad things about that, right? Like lithium mining is apparently not good for people.
Wow.
What's that? What's that?
My 5-year-old cousin of mine.
Your 5-year-old cousin, the mine, disagrees with me? But supposedly, like there was a story about 2 or 3 years ago about a Chinese company creating an alternative to lithium-ion, and I think it was sodium-ion batteries or something. And supposedly, they were having about 70% of the energy density of the lithium batteries, and they were supposedly going to be able to be manufactured with the same techniques as the lithium batteries. So my question is, was that a fake story? I mean, I don't know. It's been like 2 years.
The owners mysteriously died.
The owners mysteriously died?
Cure for cancer, mysteriously died. Just, they were found.
Well, the cure for cancer, what's the cure for cancer? I guess I better not give my cure for cancer joke. Let's see here. Although the cure for cancer would involve the most ultimate choice of running mate for Donald Trump. Can you tell me what that would be? Well, who would be the optimal choice of vice presidential running mate for the Donald?
Jack Black.
Jack Black. That might be better than my answer. But Jack Black can't cure cancer with his tears. Does Jack Black's tears cure cancer? No. Jack Black tears do not cure cancer. Whose tears cure cancer? Chuck Norris. Very good. But what's the catch, of course? Chuck Norris never cries, of course, but let's hear. Wait a minute. Do Chuck Norris jokes not land anymore?
I think so.
Whoa. You guys don't know who Chuck Norris is? Dudes. What? Oh, this is troubling.
He's going down.
Pendulum made of uniform rod, length L, and mass M. If let go from theta equals to 90 degrees. All right, so let me draw a picture. So here's the pivot point, and here is, that was supposed to be uniform, I tried. So here's theta, right? And I'm asking, it's let go from up here, right? Theta equals 90 degrees. And my question is, what's the speed of it when it gets down to here? What's omega f? Now we're assuming that it's pivoting on a pivot point which doesn't, it has no friction, like it's a smooth pivot point. So this is why I brought this silly pool stick. In part is to try to, visualize this. So if you can imagine, what? Oh man.
Sir, I think the friction between your hand and the stick hit 0.
Yeah, I know. Ah.
I hate being limitation.
Anyway, so if you can imagine, like that, like how fast does it swing? Anyway, something like that. And yes, of course, I am pinching it so I don't drop it that time. So yeah, not quite true to the theoretical constraints of the problem. But the thing to do here is to conserve energy, right? So what's the story? Energy initially is equal to energy finally. And so we need to think about the center of mass in this situation, all right? So the center of mass, let's let y be where the center of mass is, all right? So, so initially I have big M G times y equals to 0, and then plus, I'm assuming it's starting from rest, I'm just dropping it, So 0 kinetic energy. At the end, I have mg times the final y plus 1/2 I omega f squared, right? There's no translational kinetic energy here because it's stuck on the pivot point. The kinetic energy is purely rotational in this scenario, right? So then what? So, in other words, the total energy is 0. And what's y here for center of mass? L, yeah, exactly. This is y is equal to minus L over 2, right? So mg minus L over 2. Because I defined y equals to 0 to be up here, right? If I defined y not to be equal to 0 up there, then however you define y, wherever you put y to be 0, you're always going to end up with the same change in the formulas. It all works out the same. It doesn't, choosing y equal to 0 there and somewhere else doesn't change the physics here. So anyway, we have 1/2. What's the moment of inertia of a uniform rod rotating around its endpoint? We talked about this. 1/3. Yeah, 1/3 ml squared. And Then we got our omega f squared there. So solve for omega f squared, what we got? Omega f squared equal to, apparently, mgl divided by 2 divided by ml squared divided by 6. Oh, that's cool. The m's cancel. So it doesn't matter what the mass of the thing is.
What are the L's? Is it just 3L?
Yeah, I think we just get 3gl. Maybe 3, not quite, no, not 3gl, 3g what? 3g divided by l. But right idea, yeah. Now that's the square of the final velocity here. So omega f is actually the square root of 3g over l. I think this is a good example of a problem that we would have probably had no hope in solving without introducing the concepts of angular momentum and angular velocity, right? Like if we tried to solve this problem just using Newtonian mechanics that we talked about before test 2, I don't think we would have made it here, right? I mean, it would have been exceedingly difficult to figure this problem out. But now it's not that hard a problem, actually, when you see how to do it, right? Here's one that's a little bit more challenging. It doesn't look more challenging, but it is actually subtle, this last example. So the idea is very similar. This last example, we imagine like holding a uniform rod at a pivot point, all right? And so again, we're going to consider a rigid rod of length L. And so it's got some kind of, pivot point out here. And like this. And there is a force, I'll call FA there. We can imagine the force of gravity at the center of mass. It goes down, mass big mg, all right? And this is theta. In that direction, theta is going to be greater than 0. And the question is, and this is, it's horizontal at time 0, okay? So for 0 less than delta, much less than 1. You could say it this way, for t equals to 0 plus. So what I mean is for very small positive times, assuming that it's at rest and horizontal before we drop it. All right? That's the context here. So for very small positive times, A, find the thing, that's not even a word. Find angular acceleration of rod. And then part B, find what the force is applied at the pivot point. Now, if you try to actually, demo this, you'll find out that it does take some force to hold the, I mean, you saw it. I didn't apply the proper amount of force a second ago, and what happened? It got loose, right? So I have to apply some amount of force here in order to let it, see, if I apply too much, it just stay like that. But, so like that. It is what it is. So now this is not uniform, obviously. That has less mass, this has more mass. But you get the idea. If I had a yardstick, that's a better demo, but I don't have one on hand.
I was just there. They're like 2 meters late.
They're in the lab. Sure. Okay, so how do we solve this problem? For part A, we need to identify torque. Torque tau is equal to I alpha, right? What's the moment of inertia for the rod? As we have discussed, I 1/3 ml squared, right? So I haven't even given numbers. It doesn't really matter. Length L. So the moment of inertia is 1/3 ml squared. What's the torque here? First of all, if the pivot is around the point, like this is the pivot point, right? So we're talking about rotation relative to that pivot point. So FA is applied at the pivot point on the object in consideration. So what's the torque from FA? It's just 0, right? FA itself does not give us a torque because it's applied at distance 0 from the pivot point. What's the torque from gravity? So here's a theorem that I haven't quite proved, which is that the torque on an extended object is equal to the torque that's produced by applying the net force to the center of mass of the object. I don't think I've quite derived that in class. I'll see if I can, maybe in a future class. I don't think it's in my notes yet either, unless I'm just missing it. So in short, it's pretty simple. The torque, we find torque from force of gravity times the radius, center mass. So that is what? The force of gravity is just mg. Where is it applied? Effectively, it's applied at L/2. So the torque is mg L/2 in this context. All right? And then, oh well. This gives us that mg L/2 is equal to I alpha, but that is 1/3 ml squared times alpha. So what's alpha? Alpha apparently is equal to, cancel the m's, and
3 has G over L.
yeah, 3g over L.
There's the 2.
Uh-oh.
That's 3/2.
You cheated me out of a 2, did you?
No, I said 3/2.
You said 3/2. All right, fine.
Let the record show.
Let the record show. Yeah, fine.
I'll put my right hand on it. It does not work.
I knew that was coming. Let's see here.
My left.
Uh-oh.
I won't get drafted. And I'll get better parts.
All right. So, part B.
Give me drafted now. I can't.
No, you're in college.
Part B. Finding FA requires a little bit more thought here. Notice that we have the mass times the tangential acceleration. Right? The mass times the tangential acceleration. What is the tangential acceleration? Well, tangential acceleration is R alpha, right? There is no centripetal acceleration because we have a fixed pivot point, all right? So the mass times the tangential acceleration should be equal to minus FA plus what? Plus mg. Now why is it minus FA and plus mg?
The direction.
The directions, right? Because FA goes up, whereas mg goes down, which is in the positive. Anyway, so that's the story there. And then, so then I can solve for FA. So FA is equal to, mg plus, or rather minus MAT, which is equal to mg minus m times r times 3g over 2l, I guess, which is equal to mg. I think I've messed up something here. Where did that r come from? I'm a dummy. What's r? R is L. Duh. There you go. And did I do anything else dumb?
I don't know, because I don't think that's right, because wouldn't it just cancel to like mg minus mg?
That's next step.
Oh. My bad. So we're talking about this right here. This is important, guys. This has to be for the center of mass. Where's the center of mass? It's not at L, right? It's at where? L over 2 for center of mass. That's the issue. And so that puts an L over 2 here, which makes us a 1 minus a 3/4, which gives us finally mg over 4. So the force on the pivot point is actually 1/4 of the weight of the rod. So I personally find part B to be very challenging if I don't have the right ideas in mind. I've gotten stuck on this problem before myself, so I just warn you, this is, technically this is example 5, which I've called example 6 today from lecture 28. Work through it for yourself, part B. Make sure you understand this because it's easy to not quite get it. So anyway, that's it. Excuse me. Mm.